In our last class, we introduced the ideal op-amp model and saw that for closed-loop op-amp circuits, the ideal model greatly simplifies the analysis that you need to do to figure out how the op-amp works. We saw at the end of the lecture, however, that just like when you have open-loop op-amp circuits, with the closed-loop op-amp circuit, you can reach saturation. And when you do reach saturation, unfortunately, the ideal op-amp model no longer holds. We're going to look at that in a little more detail in today's lecture with an example. After that, we're going to start introducing other types of closed-loop op-amp circuits besides the inverting amplifier, which is what we've focused on so far. But let's start by talking about modeling and analyzing op-amp circuits operating in saturation. When a closed-loop op-amp circuit is in its linear or non-saturation region of operation, we saw that there are two very useful approximations that we can use to simplify the circuit. One is the virtual short circuit approximation, where the voltage at the inverting terminal tracks the voltage at the non-inverting terminal, so they're virtually the same thing. The other is that the current into both the inverting and the non-inverting terminals of the op-amp is going to be virtually zero. Now let's see what happens when the op-amp is in saturation. When an op-amp is in saturation, it's different than when it's in its linear mode, because in saturation, we know what the output voltage is. It's either going to be plus Vsat or minus Vsat. But what we're also going to see is that the virtual short circuit approximation no longer holds. So what we're going to have to do is, rather than assume that V minus equals V plus and solve for V out, we know V out, and we need to solve for V minus by performing a KCL at the inverting terminal of the op-amp in order to find it. So once again, when a closed-loop op-amp circuit is operating in saturation, the virtual short circuit approximation no longer holds. Even though the virtual short circuit approximation does not hold in saturation, the other approximation that we use in ideal op-amps does hold. And that is the fact that the currents into the inverting and non-inverting terminals are still going to be zero even in saturation. So let's look at this example here. Once again, this is an inverting amplifier, and the gain we can get from these two external resistors. The gain, G, the closed loop gain, is equal to minus 5. And we're asked to find what is the value of V minus in this inverting amplifier operation. What we see here, because the input is 4 volts, the desired output would be 4 volts times minus 5, which is negative 20 volts, which is beyond the saturation voltage. Saturation voltage, we are told, is plus or minus 14 volts. Why is it plus or minus 14 volts? Because we're probably powering this op-amp with, let's say, plus and minus 15 volts. And so the saturation voltage was something like 14 volts. So because this op-amp wants to go to minus 20 volts and it can't, what we know is that the output voltage is going to be negative 14 volts. It's going to clip at negative 14 volts. It's not going to go all the way down to negative 20. It's going to stop at minus 14. What we also know is that the virtual short circuit approximation does not hold. This means that V minus does not equal V plus. Instead, we now solve for V minus. How do we solve for V minus? We do KCL at the inverting terminal, with the unknown being the voltage here, V minus. So if we do KCL at the V minus node, what do we get? The current to the left is V minus 4 volts over 20 kilo ohms. The current to the right is what? 0 amps. Once again, this ideal property of the op-amp still holds. The current into the inverting and the non-inverting terminals is going to be 0 even in saturation. The third current, the current going up here, is what? V minus negative 14 volts over 100,000. So once again, just like when the op-amp is in linear mode, we do a KCL equation at the inverting terminal. What's different here, though, is the unknown is now V minus rather than V out. If you look back when we first looked at the inverting amplifier, we knew what V minus was. We set it equal to V plus or 0 volts, and we solved for V out. In saturation, it's the other way around. We know V out, and we're solving for V minus. Anyway, to complete the equation, the sum of those currents has to be 0. We can now solve for V minus. Let's factor out the V minus. V minus times what? 1 over 20,000 plus 1 over 100,000 equals, bringing to the other side, we have 4 over 20,000, and we have this is tricky now, you have a minus and a minus, it becomes positive, but when you bring it to the other side, it becomes minus again. So you get minus 14 over 100,000. You work out the math, you get V minus times 6 over 100,000, getting a common denominator, equals, on the right-hand side, getting a common denominator, 6 over 100,000. Solve for V minus, you get V minus is equal to 1 volt. So what we see, when we are in linear operation, V minus equals V plus, 0 volts, and V out varies. When we're in saturation, V out is fixed at the saturation voltage, and V minus changes. So here's a summary of that. How do you know whether it equals positive or negative VSAT? It depends upon this input signal. If the input signal is a positive voltage and you have an inverting amplifier, the output voltage will be negative VSAT. If the input voltage was negative, because the gain is negative, -5 specifically, the output would be at positive VSAT. So bottom line, when you have an op-amp in saturation, you still do KCL at the inverting terminal, but the unknown now is the V minus voltage, and the output voltage is now known, either plus VSAT or minus VSAT. At this point, we've focused on the inverting amplifier when we've looked at these closed loop op-amp circuits. What we're going to talk about now is a whole bunch of other useful op-amp circuits. We call these canonical op-amp circuits. What these are other standard closed-loop op-amp circuits that are commonly used in a variety of applications. The first one was the inverting amplifier, which of course we looked at already. Now we're going to talk about the non-inverting amplifier, which, as you can guess, is going to give us a gain that is positive rather than negative. Then we're going to look at a very strange circuit called a voltage follower or buffer circuit and see how it's used. Then we're going to look at a summing amplifier, specifically an inverting summing amplifier. Then we're going to look at a subtracting amplifier and a special case of that called a difference amplifier. And finally, we're going to look at a level shifting amplifier. In all of these examples, we're going to use general values for the external resistors, R1, R2, etc., so that you can see how the choice of these resistors can give us whatever type of equation that we're looking for. So let's start with the non-inverting amplifier. If you look at this, you're going to see it's fairly similar to the inverting amplifier with two differences. The first difference is your input signal Vin is not applied to the inverting terminal, but it's applied to the non-inverting terminal. The second difference is the resistor R1 coming off the inverting terminal is grounded. So once again, an inverting amplifier, Vin is attached to R1, and V plus is grounded. In a non-inverting amplifier, Vin is attached to the non-inverting input, the V plus terminal, and R1 is grounded. Let's analyze this circuit. First thing we do in the algorithm is we find V plus, the voltage at the non-inverting input. It's pretty simple here. V plus is equal to the input voltage. And then, by virtue of the virtual short circuit approximation, we know that V minus equals V plus equals Vin, once again because of the virtual short circuit approximation. So the voltage at this point is also Vin. Then, just like in the inverting amplifier, we now do KCL at the inverting input. That current plus that current plus that current equals 0. So KCL at the V minus node, and we're going to solve for V out. So the current to the left is what? V in minus 0 volts over R1. The current to the right, the current into the inverting terminal, is 0 amps in an ideal op amp. The current going up is what? Voltage V minus, which in this case is V in, minus V out over R2. The sum of those three currents has to be equal to 0. So now let's solve for V out. We get V out over R2 equals V in times what? 1 over R1 plus 1 over R2. Solving for V out, we get V out is equal to V in times R2 times 1 over R1 plus 1 over R2, which we could rewrite as what? We could rewrite it as 1 plus R2 over R1 times V in. And this is our closed loop gain G. So for a non-inverting amplifier, the gain G is equal to 1 plus R2 over R1. A couple things to note about this gain. First off, the gain is positive. In an inverting amplifier, the gain was negative R2 over R1. Now it's 1 plus R2 over R1. It's always positive. Positive, meaning it is a non-inverting amplifier, which means if V in is positive, V out is positive. If V in is negative, V out is negative. The other thing that we note is that the gain G is greater than 1. This is different from the inverting amplifier case. In the inverting amplifier case, you could get a gain with a magnitude greater than 1 or less than 1. If R2 was less than R1, your gain would be something like negative 1/2, negative 2/3, whatever. For the non-inverting amplifier, however, in this configuration, the gain is not only positive, but it's greater than 1 because it is 1 plus R2 over R1. Suppose you want to gain less than 1. What you need there is a variation. What you do in this variation is instead of connecting V in directly to the non-inverting terminal, you connect V in to a non-inverting terminal through a voltage divider. Put a resistor here called R3, a resistor here called R4. Put that to the non-inverting input, and then the inverting input, we still have our resistor R1 connected to ground, and we still have our feedback resistor R2 connected between the output and the inverting terminal. And of course, V out is measured with respect to ground like that. In this variation where we have this voltage divider here, the very first step changes. V plus is no longer equal to V in. What is V plus now? Well, we have a voltage divider. Remember, there's no current here. So this current is 0 into this terminal here. So R3 and R4, even though they're technically not in series, are basically in series. All the current going through R3 has to go through R4. So what does that mean? That means that the voltage here, V plus, we can get from voltage division. V plus is approximately equal to what? R4 over R3 plus R4 times V in. So the voltage at the non-inverting terminal is no longer V in, it's now R4 over R3 plus R4 times V in. If you then take that result and plug it back into the KCL equation up here, we would get this variation in the gain. We would get that V out, in this case, is equal to R4 over R3 plus R4 times 1 plus R2 over R1 times V in. So now our gain G is that expression here. This expression here is always positive, just like in the previous case, but now it can have a magnitude less than 1. So we have two different non-inverting amplifier configurations. The first one is where we attach our input signal directly to the non-inverting terminal, and the gain is going to be 1 plus R2 over R1. In the second situation, we put a voltage divider there, and this allows us to get a gain that is less than 1, but still positive. Let's do a couple examples. First example, we want to design an op-amp circuit where the output voltage is 12 times the input voltage. So this is a positive gain, so we want a non-inverting amplifier. Basically, we want 1 plus R2 over R1 to be 12, or you want the ratio of these two external resistors to be 11 to 1. So one possible circuit you could build is you connect V in directly up to the non-inverting input terminal. Then we have these two resistors here, R1 there, R2 there, and then V out is measured with respect to ground. R1 is grounded, and we want the ratio of R2 to R1 to be 11 to 1. So one possible solution would be an 11 kilo ohm resistor there and a 1 kilo ohm resistor there. I should point out that this is not a unique solution. As long as R2 is equal to 11 times R1, we're going to get a gain of 1 plus 11 or 12, which is what we want. The other thing I want to remind you is we typically want to choose these external resistors to be the hundreds of ohms to the kilo ohms to the tens of kilo ohms to the 100 kilo ohm range. Remember, there are these internal resistances to the op-amp that we're sort of ignoring. There's this R in there, and there's an R out there. We want these external resistors to be very small compared to R in, and we want these resistors to be very large compared to R out. We saw that a couple lectures ago. Once again, as long as you choose these external resistors somewhere in the kilo ohm range, you're going to be safe. So this circuit gives us a non-inverting amplifier with a gain of 12. Suppose you want now an op-amp circuit with a gain is not 12, but 1/4. This is a gain less than 1. So going back to the previous page, we need to use this variation circuit. We cannot use the standard non-inverting amplifier because you cannot get a gain less than 1. Instead, we have to use this variation with this voltage divider connected to our input signal. The reason being is because 1 plus R2 over R1 equal to 1/4 is a problem. You can't do it. You'd have to have a negative resistance. So instead, the solution is to use our variation of the non-inverting amplifier. What we want is our gain G is going to be what? It's going to be R4 over R3 plus R4, where R3 and R4 are the resistors in this voltage divider, times 1 plus R2 over R1. And we want that product to be 1/4. So you have lots of choices here. As long as the product equals 1/4, we're okay. So what we can do is let's choose, for example, we'll let R4 over R3 plus R4 be 1/8, and let 1 plus R2 over R1 be 2. This is not unique. Rather than 1/8 times 2, I could have done 1/16 times 4. There are an infinite number of different products we could do to get 1/4 as our final answer. In this example, I'm using 1/8 and 2. So if R4 over R3 plus R4 is equal to 1/8, how do you get that? Well, we could, for example, set R4 equal to 10 kilo ohm and R3 equal to 70 kilo ohm. So one solution, V in here, have a 70 kilo ohm resistor, a 10 kilo ohm resistor. We're going to feed that to the non-inverting input of our op-amp. The voltage here, V plus, is equal to what? V in over 8. Then we want to choose the other two resistors. For that one, we want what? We want 1 plus R2 over R1 to equal to 2, or R2 has to equal R1. Once again, infinite number of solutions here. Let's set R2 equal to 10 kiloohms and R1 equal to 10 kiloohms. Once again, by setting these two resistors the same, we guarantee that the gain of this part of the circuit is 2, and then when you multiply it by this 1/8, which comes from this part of the circuit, we get our overall gain of 1/4. So V0, which is the voltage at the output terminal with respect to ground, is going to be what? Vin over 4. So in these two examples, we see how to handle non-inverting amplifiers with a gain greater than 1 and how to handle non-inverting amplifiers with a gain less than 1. And in both of these cases, the answer is not unique. There are many different resistor combinations that can give us these gains that we want. The second example raises a good question. If you want to gain less than 1, why not just something like this? If you wanted the output voltage to be 1/4 of the input voltage, why not something as simple as this? If you just use a simple voltage divider and set V0 equal to the voltage between these 2 points here, from voltage division, you get 10 over 10 plus 30. That's 10 over 40, or 1/4, times Vn. So you might ask yourself, why not that? We're going to see why in a minute. Because it does make sense to just use voltage divider. If you want to gain less than 1, just use voltage divider. Why put an op amp in there at all? Obviously, if you want to gain greater than 1, you have to use an op amp because a voltage divider can't give you a bigger voltage. But we already have a voltage divider to give us a smaller voltage, so why would you use an op amp in this situation at all? We're going to sort of see that in our next canonical form. So now we're going to look at the voltage follower, also called a buffer circuit. This is probably the strangest of the op-amp circuits because it's very minimalistic. And when we see the relationship between V in and V out, you might ask yourself why use this at all. But we'll see in a minute that this is actually an extremely useful circuit. In a voltage follower circuit, we're connecting V in directly up to the non-inverting input terminal, just like we did in a non-inverting amplifier. But as far as the feedback goes, we're not going to put any resistor at all between V out and the inverting input terminal. In other words, we're going to set R2 equal to 0. Furthermore, we're not going to have a resistor R1 connected to ground. In other words, we have no resistor here. So another way to think about this is R2 is equal to 0 ohms and R1 is equal to infinity ohms. You have a short circuit for this feedback resistor and an open circuit connecting to ground. This is called a voltage follower or buffer circuit. Well, let's see what the output is in this case, and then we'll see why we would want to use this. So the way you analyze this is the same way we analyze the inverting amplifier and the non-inverting amplifier. We start by finding what the non-inverting voltage is. V plus, because it's connected directly to our input signal, is going to be equal to Vin. And then because of the virtual short circuit approximation, the voltage at the inverting terminal is the same as the voltage at the non-inverting terminal, or Vin, because of the virtual short circuit approximation. So the voltage here is also Vin. But because of this wire here, V out is also equal to that. So we get the third part, V out is just the same as V minus, is just the same as V plus, is just the same as V in, and we get this amazing equation. The output voltage is equal to the input voltage. And the first thing you may ask yourself is, why do you need a circuit like this? If you want an output voltage to equal an input voltage, why not just connect your input signal directly to what we're calling our output terminals and call it a day. There's our answer. Why can't you just use this? The answer is because of loading. So we'll look at that on the next page here. So why do you want to have this voltage follower circuit or a buffer circuit? Let's imagine that we have a practical voltage source. So a practical voltage source has a nominal value Vin and an internal resistance Rs. So now this is our practical source, like that. So it's a battery, for example. Suppose you're now driving a load with the resistance RL and you want to measure the voltage V out across the load. What is the voltage V out? Does it equal V in? No, because of loading, we get from voltage division that V out is going to be RL over RL plus RS times V in. So what we get, the output voltage is RL over RL plus RS times V in. So V in is what we call the nominal voltage of the source. And V out is what we call the terminal voltage, what we actually get. And what we see is that V out is going to be less than V in, and this is what we call our loading effect. In fact, we saw earlier this semester, unless RL is much, much greater than RS, V out is not going to be close to V in. What happens, as current comes from the source to drive the load, you get a voltage drop across this internal resistance. This is lost internal voltage. And the voltage you have available to drive the load is less than what you want. And that is because the source is providing the current to drive the load and it's losing some voltage through its own internal resistance. That's a bad thing. Let's look what happens if instead of connecting the practical source directly up to the load, you connect it up to a buffer circuit first. So we still have our practical source here. But now we have in between our voltage follower or buffer circuit. Let's see what happens here. What do we know about the current going into the non-inverting terminal of the op-amp? It's 0. So what does that mean about the current flowing through this internal resistance of the source? It's also 0. That means that the voltage at the non-inverting terminal is going to equal the nominal source voltage, or V in. Then, by nature of the virtual short circuit approximation, the voltage here is also V in, the voltage here is also V in. So what we see, if you use the buffer circuit, is that V out equals V in. We have no loading. You may ask, well, what's happening here? Well, let's think about where the current is coming from in the two cases. In the first circuit, the current is coming from the source itself through the internal resistance to drive the load. In the second case, where is the current itself coming from? It's actually coming from the power supplies powering the op-amp. Remember, we have VCC and VEE here, plus or minus 15 volts, whatever. So what's actually happening in the second case, the current is not coming from the practical source. The current is actually coming from the power supply through the op-amp to drive the load. So when you have a buffer circuit, the input signal is just providing a voltage reference. It's actually not providing the power to drive the load. So this is the significance of the voltage follower or buffer circuit. Basically, the buffer circuit isolates the source from the load so that you don't get loading. You're not getting something for nothing because you're still providing the energy, but the energy is coming from the power supplies themselves, not from the practical sources. And so you don't have to worry about loading from the source to the load. So you'll find many cases where you want to drive a load that has a low resistance, and so RL is not much larger than RS. And in order to do that without getting loading, you need to put a buffer in between so that you can isolate the input signal, the practical source, from the load. All the amplifiers we looked at so far, the inverting, the non-inverting, and the buffer, basically had one input signal. One of the best features of op amps is it allows you to combine signals together. And we're going to do this here with what we call an inverting summing amplifier. So in this case, we have two different signals. We have VB connected through resistor RB, and we have VA connected through resistor RA. Both of those are connected to the inverting input terminal. Then we have a feedback resistor R2 between the inverting terminal and the output terminal. That's our negative feedback. And we're going to ground the non-inverting terminal. So this looks sort of like the inverting amplifier, except instead of just one source connected through one resistor to the inverting terminal, we have two different sources connected through two different resistors to the inverting terminal. Let's analyze this circuit. The way we analyze it is the same way we analyze every other ideal op-amp circuit. We start by looking at the non-inverting terminal and determine what its voltage is. In this case, it's pretty simple. The voltage at the non-inverting terminal, V+, is just going to be 0 volts because it's connected directly to ground. And then, because of the virtual short circuit approximation, V- is also equal to 0 volts. So we have 0 volts at that terminal and 0 volts at that terminal. Now what we do, the second step in the algorithm, is we always apply KCL at the inverting terminal. So inverting terminal is right here. We're going to sum up that current plus that current plus that current plus that current. Basically, we have this node here, and we're going to sum the currents leaving that node, set it equal to 0. So KCL at the V- node, current going down here is 0 minus VB over RB. Current going here is 0 minus VA over RA. Current going here is 0. Once again, the current into the inverting terminal of the op-amp is always 0. And the current going through R2 is 0 minus V out over R2. The sum of all those currents has to equal 0. Let's solve for V out. V out over R2 equals what? It's negative VA over RA minus VB over RB. Solving for V out then, we get V out is equal to minus R2 over RA times VA minus R2 over RB times VB. What we see is that the ratio of R2 and RA give us the gain associated with that input, and we see the ratio of R2 to RB give us the gain for that input. And what we see is that the output is an inverted weighted sum of VA and VB. Inverted because we have a minus sign here and here, so that's the inverting part. Weighted because these gains here, A and B, can be different, and it's a sum because we're adding them together. So once again, V out is an inverted weighted sum of VA and VB. And once again, we can pick RA and RB to get whatever desired gains we want. This example shows it with just two inputs. We can actually have as many different inputs as you want. Basically, each input gets connected to a different resistor, all the resistors together get fed into the inverting terminal. So you could have VA there, VB there, VC there. You could have as many different terms as you want. You can add together. And then just make sure that the non-inverting terminal is grounded. And then you have your feedback resistor R2 here. And then V out is measured with respect to ground. So let's do an example. Let's design an op-amp circuit where V out is negative 4V1 minus 10V2. So imagine you have two input signals, V1 and V2, you want to mix together. And we want to amplify the first one by 4 and the second one by 10. Basically, we want the ratio of R2 to RA to be 4, and we want the ratio of R2 to RB to be 10. So we have infinite number of choices we can choose. We can pick R2 to be some convenient value, maybe 20 kiloohms. Once again, it's somewhat arbitrary. Once R2 is fixed, though, that fixes what RA and RB have to be. RA, 5 kiloohms, because 20 over 5 is 4. And RB in this example would then have to be 2 kiloohms, because 20 over 2 is 10. So one solution would be this circuit here. We ground our non-inverting terminal. Our inverting terminal, we connect up through two resistors. One resistor is connected up to our first input, let's call it V1 of t. And that resistor is going to be a 5 kiloohm resistor. Our second resistor is connected up to our other input signal, V2 of t. Its value is going to be 2 kiloohm. And our feedback resistor in this example was 20 kiloohms. So V out is now equal to what? Negative 4, 20 divided by 5 is negative 4 times V1, minus 10, 20 over 2, times V2. Notice in this inverting summing amplifier, we're summing V1 and V2 together, but then we're inverting it. So both of them are going to have a negative gain. And that's because they're connected through resistors to the inverting amplifier. And with our previous examples, this is absolutely not a unique solution. There are many, many different resistor combinations that could give us this expression here. The key is you want to choose resistors that are sort of middle values. Something in the kiloohm, tens of kiloohms, hundreds of kiloohms range always work out well. What we see here is if you connect both of your signals to the inverting input of the op-amp, you get an inverting summing amplifier. What happens if you connect one of the inputs to the inverting terminal of the op-amp and the other input to the non-inverting input terminal of the op-amp? There we're going to get a subtracting amplifier. So we'll look at this one now. So this amplifier is similar to the other ones, but once again slightly different. We're going to take our first input signal, VA, connect it through a resistor R1 to the inverting terminal of the op-amp. Then we're going to take our second signal, VB, connect it through a couple resistors, R3 and then R4, to the non-inverting terminal. Let's analyze this circuit and see what we get. First thing we do is we want to find V plus. What is V plus? From voltage division, V plus is simply R4 over R3 plus R4 times VB. So V plus is R4 over R3 plus R4 times VB. It's voltage division. Once again, R3 and R4 are technically not in series because of this wire here, but because there's no current flowing through that wire for all intents and purposes, we say that R3 and R4 are in series, so we can still use the voltage division equation. Second step is we know that V minus is going to equal to V plus because of the virtual short circuit approximation. So the voltage here is also going to be R4 over R3 plus R4 times VB. Then to find an expression for the output, we do KCL at the inverting terminal. This current plus this current plus that current has to be 0. The current going to the left is what? R4 over R3 plus R4 times VB. All of that minus VA over R1. Current going to the right is 0. Current going up is what? R4 over R3 plus R4 times VB. Voltage on the other end is V out divided by R2. All of that has to equal 0. If you solve for V out and do some math, you get the final expression that V out is equal to minus R2 over R1 times VA plus 1 plus R2 over R1 times R4 over R3 plus R4 times VB. In other words, that is going to be some number B, and that is going to be some number A. And so what we get is that V out is going to be some gain V times VB minus A times VA. It's a subtracting amplifier. The output is the signal VB multiplied by some constant B, which you pick through the choice of these resistors, minus A times VA, where A you pick by the choice of those resistors. One thing we need to note here is that the gains A and B are not completely decoupled. What do I mean by that? If you notice, R2 and R1 show up in both equations. It shows up there for A and shows up there for B. So because of that, what we have is that B always has to be less than or equal to A plus 1. You cannot get B greater than that. There's a special case of the subtracting amplifier. If you set the ratio of R4 over R3 equal to R2 over R1, what we're going to see from the second term is that 1 plus R2 over R1 times R4 over R3 plus R4. If you take that right term there, divide everything by R3, that now becomes what? 1 plus R2 over R1 times R4 over R3 is just R2 over R1. And R3 over R3 is 1. R4 over R3 is equal to R2 over R1. We get that. And what we see is this denominator cancels with that. We just get R2 over R1. So in the special case, what we get is that V out is equal to minus R2 over R1 times VA plus R2 over R1 times VB, or R2 over R1 times VB minus VA. We call this a difference amplifier. It's a special case of a subtracting amplifier where the two gains B and A are going to be the same. So once again, choosing the ratio of R2 and R1 determine what the total amplification would be, but it's always then the difference between VB minus VA multiplied by that amplification. Let's finish up this lecture with two more design examples. Both of these are related to the subtracting or difference amplifier. The first one is we want to design an op-amp circuit where the output is 4V1 minus 10V2. So basically we're subtracting V2 from V1, but we're scaling them differently. So basically this is our gain capital B, and that's our gain capital A. And note that B is less than or equal to A plus 1, which we determined here had to be the case. So we're okay. What happens when you have these subtracting amplifiers to design, you always design for the inverting gain first. Specifically, what do we want? We want minus 10, the inverting gain, should be minus R2 over R1. We saw that right there. Capital A is going to be 10. So in other words, we want R2 to be 10 times R1. So we can set R1 equal to 10 kiloohms and R2 equal 100 kiloohms. It is not unique. Once you design for A, then you can design to get the B that you want. Here, we want our non-inverting gain of 4 to be what? It's 1 plus R2 over R1 times R4 over R3 plus R4. But this is where we see that these two are not totally decoupled. R2 over R1 we already saw that has to be 10. That means then that R4 over R3 plus R4 has to equal what? 4 over 11. This is why you want to design for A first, because what you choose for A is going to show up in your expression for B as well. So in this case, we want the ratio of R4 over R3 plus R4 to be 4/11. Once again, there are infinite number of solutions. A logical one would be setting R4 equal to 40 kiloohms and R3 equal to 70 kiloohms. So if you were to draw this, the non-inverting terminal gets connected through R3 and R4. R4 gets connected to ground. There's our 40 kiloohm resistor. R3 is here. And then connected to the other end of that is our input, in this case V1. This is the input that's not getting inverted. Then the second half connected to the inverting side of the op-amp. R2 we said was 100 kiloohms. R1 was 10 kiloohms. And V2 is connected here. And so Vout is measured between that output terminal and ground. And what's it going to be? It's going to be our input V1 connected to the non-inverting terminal, so it has a positive gain, and our input V2 connected to the inverting terminal, it's going to have our negative gain. And Vout is going to be 4V1 minus 10V2. And as with our other examples, this is absolutely not unique because it's just the ratio of the resistors that really matters. In our last example here, we're asked to design an op-amp circuit where the Vout is equal to 4 times V1 minus V2. This now is what we call a difference amplifier. It's a special case of a subtracting amplifier. It's a subtracting amplifier where both inputs are going to have the same gain. And now the gain is 4. So what we want is we want the ratio of R4 to R3 to be the same as the ratio of R2 to R1, and that ratio should be whatever this gain is. This is a special case that we looked at down here. Since we want a gain of 4, there's an infinite number of solutions. One logical solution is to set R4 and R2 both to 40 kiloohms and set R3 and R1 to 10 kiloohms. If we then draw this circuit, R3 and R4, R4 is connected to ground, R3 is connected to the input that we don't want to invert. That's going to be V1. Then on the inverting side, we're going to have R2, 40 kiloohms, R1, 10 kiloohms, and then our inverting input, V2, gets connected there. Once again, the input that you don't want subtracted is connected to the non-inverting terminal through resistors. The input that you do want to get subtracted is connected to the inverting terminal through resistors. And once again, by making this ratio the same as that ratio, we get a difference amplifier. So what we've done in today's lecture is looked at these canonical forms. We looked at the non-inverting amplifier, we looked at the buffer or voltage follower amplifier, and then we looked at the inverting summing amplifier where you could sum 2 or more signals together, and finally we looked at the subtracting amplifier and the difference amplifier, which allows you to subtract 2 signals from each other. So all of these are slight variations of the standard inverting amplifier configuration. You can put the signals at the inverting side or the non-inverting side, both sides, to get all kinds of combinations. And in each of these cases, we have these equations that we've developed. Once you have these equations, if you want to memorize them, you then don't have to worry about going through the analysis each time. Just memorize the equation for the subtracting amplifier, the difference amplifier, the inverting summing amplifier, and the non-inverting amplifier. Buffer amplifier doesn't really have an equation you need to memorize, but you need to remember that that's used when you don't want to have the output loading the input signal. We'll pick this up next time. We'll look at one more canonical amplifier called the inverting level shifting amplifier, and we'll see how that one's used, and then talk about multi-op amp circuits. Have a good day.